Hi, in this video I'm going to talk about the bulk modulus, and specifically I'm going to try to answer how important is it to know very well what the bulk modulus is for a finite element simulation. You always need to specify a bulk modulus value for your material models, but does it really make a difference? And if it does, how much difference does it make? So to investigate this, I will first take a look at a simple loading mode. I'm going to take a look at uniaxial tension in this case. I'm going to try a few different bulk modulus values to see what difference it makes, if any. And then I will run a finite element simulation with two different bulk modulus values. Again, trying to investigate what difference does it make, if any. And finally, I'm going to talk a little bit about how you would measure the bulk modulus if you need to measure it in using experimental tests. So let's start by looking at a simple loading mode. So to investigate this, I'm going to use MCalibration, and MCalibration is very easy to plot and compare different material model behaviors. I have three different loading modes, and I have one material model here. I'm going to compare the results now for different bulk modulus values. So I'm going to pick 500, I select this load case, and I just run it. I run that only. And here's the stress strain response when the bulk modulus is 500 megapascal. The material model is a 3-network material model suitable for a stiff thermoplastic material. But what if the bulk modulus wasn't 500? What if it was twice as high? So a substantial difference. I pick this one and I run this load case now, and you'll see that, whoa, the curve doesn't change. So but 500 or 1000 doesn't really make much of a difference. How about 2000? So 2000 megapascals, I pick the first load case, I run that one. And again, we can see that it just looks like one curve. In essence, the bulk modulus does not influence the response in any significant way for thermoplastic materials in uniaxial tension. How about rubber materials? I will investigate the response of rubber materials in a very similar way. I have MCalibration with the Bergstrom-Boyce material model. I have three load cases. I'm going to start with 100 megapascal as a bulk modulus. I'll run this load case first. Here's the stress strain response at 100 megapascals. If I make it 5 times larger, 5 times, it's a huge difference, right? We'll see what difference it makes. Virtually no difference. How about if I make it 2000 instead of 500? It's a huge difference compared to the first one, and I don't even see the curve. It's behind the other curves. So what we see is that the bulk modulus really does not influence the stress strain response in uniaxial loading for either thermoplastics or rubbers or for any material for that matter, really. But what about the multi-axial loading mode? What if we do a finite element simulation? I created a simple Abaqus finite element simulation of an O-ring, as you can see here, and that sits in a groove with a little opening on one side. And you can see the mesh that I used here. And I just want to investigate what happens in this case when I try different bulk modulus values. This is multi-axial after all, it's not just a tension test. This is axisymmetric, and I'm using a viscoelastic Bergstrom-Boyce material model. The boundary conditions are very simple. I apply pressure on the bottom here just to illustrate what happens. May not be the most accurate way to do it in real life, but it would allow us to investigate the influence of the bulk modulus. And the results are here. On the figure to the left, I look at the response when the bulk modulus is 400 megapascal, and on the figure to the right are the results when the bulk modulus was 2000 megapascals. Very big difference, 400 to 2000. But if you look at the maximum compressive strains, they are pretty much identical. The maximum tensile strains are also pretty much identical. The mesos stress, the maximum mesos stress, is a little different, but very similar after all. Look at the contours of the compressive strains here, maximum principal compressive strain, they're also very similar. So we can see, even in a situation like this where we have a highly confined geometry, high pressure, large deformations, the bulk modulus doesn't make that much difference. So there are cases where the bulk modulus does make a difference, but they're very hard to come by. Most of the time it really doesn't make that much difference what value of the bulk modulus you pick. If you want to measure the bulk modulus, there are different ways to do it. Here are 3 ways that I've used in the past. You can use digital image correlation, DIC, of a tension test, for example. So in a DIC experiment, you measure the whole field of strains, so you can calculate from the DIC results the Poisson's ratio from which you can get the bulk modulus. This tends to be not super accurate at small strains, but it's a way to approximate the bulk modulus for your material. Another way to do it is to do a pressure volume temperature test. Specialized equipment that directly gets this behavior from which you can then calculate the bulk modulus. And finally, you can do a confined compression experiment, and I have a schematic down at the right here from my book that illustrates one way to do it, where you basically confine the cylinder and you look at the pressure volume response from which you can get the bulk modulus of your material. So, as we've shown here, the bulk modulus is always needed in your finite element simulations, but very rarely does it make a big difference. Often it's good enough to guess it, as long as your guess is reasonably good. And here's a little table that I find helpful. It shows you for a given Poisson's ratio what is kappa divided by the Young's modulus. And you can see that a Poisson's ratio of 0.45 gives you a kappa that's about 3.3 times the Young's modulus. It gives you a little bit of a feeling for how kappa should be. In MCalibration, it's also very easy to specify the Poisson's ratio in a Poisson's ratio load case and then search for kappa as part of your parameter optimization. If you need to, you can measure it, but most of the times you actually don't need to.